All right, friends, welcome back. Today we're going to start in on our discussion of acids and bases. And this is not going to go necessarily the way you think, because we are not going to be calculating stuff. There's going to be no ice tables. Actually, my missionary son that took, my missionary son that took 105 before his mission is like, Dad, I want to do an ice table. Can you give me a chemistry problem? And between you and me, 105 wasn't that a great experience for him, so I'm not sure why he wants to do ice tables. But anyway, I understand that all of you do not, and you will not see them in this class. Instead, we're going to use acidity and basicity as a framework to understand why reactions happen and to predict whether they'll be favorable or not. A couple of things you need to know, just real briefly, and this is probably stuff that you've seen before. So for every acid, we're going to put it in equilibrium with water, and we're going to measure the strength of that equilibrium. Now, you learned about that in 105, 106 as acid dissociation. The acid wants to lose its proton. That is an oversimplification of what's actually going on in an acid-base reaction, which you now know. For example, you know that in an acid-base reaction, water, as the nucleophile, attacks the sigma star of the bond between the hydrogen and whatever it's bonded to, and breaks the sigma bond. And that gives you two products, A minus, which is the conjugate base of the acid, which is HA, and then you get H3O plus, which is the conjugate acid of water, which is your base. Okay? So we're going to abandon the fiction, useful though it was, that a hydrogen would dissociate, and just realize that in water, the hydrogen goes somewhere. Where does it go? It goes onto water to become hydronium. Okay? I feel like that's not such a big stretch, but it may involve a change in your thinking. Now, if you were to write the equilibrium constant for that reaction, you would come up with something like this, concentration of H3O plus, which you previously represented as H plus, A minus, and then HA with the concentration of water here. Why are we putting it in equilibrium? Because it's involved. We're going to just gloss over entirely anything you may have been told about pure substances and activity and so on. Turns out the concentration of water is really high in a water solution. You can do the math, and it's like 55 molar, so it doesn't change very much at all when some of it becomes H3O plus. So we're going to treat that as essentially constant, and we're going to fold this number, the concentration of water, into this equilibrium constant. Basically multiply both sides of the equation by the concentration of water. And that gives us a new constant, Ka, which is this so-called acid dissociation constant. Tells you how strong an acid is relative to water, right? If this number is really big, that tells you that the acid loses its proton to water. If this number is really small, it tells you that the acid doesn't lose its proton to water. Okay? But Ka can vary over many orders of magnitude, 10 to the minus 40 all the way to 10 to the 15 or something like that. And because we get tired of writing all those exponents, we instead define a logarithmic scale for Ka, and that's pKa. Okay? Two things you need to know about pKa. It's the logarithm of Ka. The logarithm is basically asking the question, what power do I have to raise 10 to get the Ka? And then the negative sign. So that changes the Ka trend, flips it. Whereas Ka, if it's really, really large, the acid is strong. For pKa, the lower the pKa, the stronger the acid. Now, you are totally welcome to forget all the math as long as you know that pKa is a measure of acid strength, and the lower the pKa, the stronger the acid. It's going to take you a while to get that. It's going to require some practice. I highly recommend you do that practice before you get in the exam. It's going to be useful if you don't have to puzzle that one out by the time you get there. Now, let's just briefly talk about why you should care about acid strength. One of the reactions we did in our descriptions of HOMO attacking LUMO involved this molecule here, which is called an alkoxide, as a nucleophile, attacking this molecule as an electrophile. And we said that the HOMO of the alkoxide was the lone pairs on the oxygen, and that the LUMO of this electrophile was the carbon iodide sigma star. So we showed electrons from iodide attacking the carbon because you're filling the sigma star, which I'm not drawing because we drew this last time, the carbon iodide bond breaks. And the products of that are a new carbon-carbon bond between the oxygen and the carbon here. And then the other product is iodide, I minus. Okay? We call iodide the leaving group because it took the electrons in that carbon iodide bond and left. It had to because the alkoxide attacked the sigma star. Now, some of you were wondering, how do I know whether that reaction was favorable or not? And that comes down to two basic considerations, one of which we're going to deal with today, and the other that we'll leave until chapter 6. So the first consideration that we're going to leave until chapter 6 is you compare the strength of the bonds that you broke versus the strength of the bonds that you formed. If you form a stronger bond than the one you broke, then the reaction tends to be favorable. We'll talk about that in chapter 6. I mean, the punchline here is that carbon-oxygen bonds are stronger than carbon-iodide bonds, and so this is a favorable reaction. But that's only part of the puzzle, one part of the puzzle, because there's one other thing that's changing, and that is that we start with an alkoxide that has a negative charge. We're going to call the alkoxide the nucleophile because that's what it is. And then versus the leaving group. Leaving group is our LG with the minus is our abbreviation for I minus. How stable is that nucleophile versus the leaving group? You could imagine that if the leaving group is more stable than the attacking nucleophile, that the reaction would be favorable, because by going from starting material to products, you're going downhill in energy. But you could imagine that if the leaving group isn't more stable than the nucleophile, that maybe the reaction wouldn't be favorable. Does that make sense? So now go ahead.
So if it gets more stable, it's more favorable?
Yeah, if it gets more stable, it's more favorable. In both cases, if the bonds you form are more stable than the bonds you broke, it's favorable. If the leaving group is more stable, if the leaving group is more stable than the nucleophile, that's more favorable. Okay? So how do we compare the stability, and this is the one we're going to deal with today, how do we compare the stability of the nucleophile with the leaving group? And there's a couple ways we can do that, but let's start with just the evidence. So it turns out one of the ways to compare the stability of things that are negatively charged is to consider the acidity of their conjugate acid, which I'm going to abbreviate as Ca. So what is the conjugate acid of the alkoxide? That's what the alkoxide would be if it had attacked a hydrogen instead of a carbon. So the conjugate acid of the alkoxide is this molecule here, which is called an alcohol. Now, as I write down names of stuff, somebody out there is wondering, so did you want me to memorize that? Is that why you wrote it down? In chapter 3, we will talk about names for organic molecules and how to talk about them. Right now, you just want to follow along and be able to, when I'm using words, you want to basically know what they mean. When we get to chapter 3, you'll learn some of the rules for talking about these molecules. At this point, like I've said before, it's like you're watching a telenovela in Spanish, and if you can pick up a few words, you're on the right path, okay? So the alcohol is the conjugate acid of the alkoxide. What do you think, what is the conjugate acid of iodide? HI, right? If iodide picked up a proton from some source. That's going to bother some of you, right? You're used to writing H on the left, so okay, that's HI. Hydroiodic acid. Now, the fact that this is called, you don't need to know that, hydroiodic acid gives you a clue as to which one is more acidic, right? But if you didn't know that, what you would do is you'd go look up their pKa's. And if you did that, you would find that the pKa of HI is like -11, whereas the pKa of the alcohol is 16. Based on what I just told you about pKa, which is the stronger acid? HI, absolutely. Stronger acid. Okay. Weaker acid. And this is actually a good time to mention something that is different about the way we will talk about acids in this class versus how you did it in 105, 106. In Gen Chem, you guys probably memorized a list of strong acids and strong bases as though strength were an absolute thing, as though you could look at an acid and say, is this a strong acid? What they were really doing is asking you to memorize a list of acids that would always lose their protons to water. That is, a list of acids that would always form H3O+, where this equilibrium constant would be really huge. And similarly for bases, strong bases, they were asking you to memorize a list of bases that would always steal a proton from water. For us, we're going to be talking about acid strength as a relative thing. So if you ask me, is that a strong acid? I'm going to say relative to what? And only then will I answer the question, if you tell me what the comparison is. So, is the alcohol a strong acid? Well, that depends. Relative to what? Relative to HI? Oh no, HI is much stronger of an acid than the alcohol. All right? So you can get rid of you can dispense with the idea of, oh, is it a strong acid or not? It's always relative to something. There's always going to be a comparison. And if you haven't found that comparison, you haven't understood the question and you need to look further, okay? All right, now we've decided that HI is the stronger acid. What does that have to do with the conjugate base? It turns out that the stronger acid has a more stable conjugate base. And equivalent or interchangeable with the idea of, oops, didn't want that to happen, interchangeable with the idea of a more stable conjugate base is the idea that this conjugate base is less reactive, less basic. Okay? So the stronger acid, the more acidic acid, the more reactive acid has the less reactive, less basic, more stable conjugate base. And the weaker acid, the less reactive acid, the less acidic acid has the stronger conjugate base. The less stable conjugate base, the more reactive conjugate base. Okay? This is a general trend. Why are strong acids strong? Because their conjugate bases are more stable. Yes?
So, basically, what you're saying here
So,
But wait, see, that's what I'm not getting.
right, so it may seem a little bit weird that I've started talking about conjugate acids because there's no acids involved in this reaction. We're using information about the conjugate acid as a surrogate to tell us how stable the conjugate base is. Because that's our real concern, is how much more or less stable is I minus than the alkoxide. And we can get that information from looking at the pKa's of the conjugate acids. Even though those acids are not involved in this reaction, those pKa numbers tell us how stable the conjugate base is. Does that make sense? Okay. Yes?
So you're saying that the iodide is less basic than the hydride acid?
Yes, I minus, no, well, yes, but the less basic is this comparison. So HI is more acidic than the alcohol. I minus is more stable, less basic than the alkoxide. All right, now, you can use that information, pKa information from a table anytime you want to make this comparison. But we don't necessarily want to be pKa table robots. We want to have an idea of the whys behind some of these acidity trends. For example, you could ask, we've concluded as a fact that I minus is more stable, less reactive, and less basic than the alkoxide. But then you could ask, but why? And is there a way to figure it out even if I don't have a pKa table? I will point out that I will give you, this is the pKa table that appears on each one of your exams and is on your problem set. We're gonna talk about it. We'll work our way through it about how to use it. But in addition to the data there, it's useful to know some of the reasons behind some of those trends. So let's just look briefly at the difference between O minus and I minus. We're going to see, as I said, this is less basic, more stable. And O minus, the alkoxide, is more basic or less stable. And we're going to talk about why. And the reasons why are basically always going to be related to two main concepts. The first is electron delocalization. Oops, I ran out of space for the end. There it is. Electron delocalization. Spreading out. The principle here is spreading out a negative charge is stabilizing to a conjugate base. And there are going to be basically three strategies for spreading out a negative charge in a conjugate base. And we'll talk about each one. The first two I'll tell you now. One is resonance. The other is size of the atom that is negatively charged. And the third one, you're going to have to wait a minute. The second factor is the electronegativity of the atom that bears the negative charge. Okay? So what are the differences between I minus and O minus in this way? Well, it turns out that if you look up electronegativity numbers, oxygen's more electronegative than iodide. But it turns out that iodide is much larger of an atom than oxygen. If you don't believe me, we can look up structures of some molecules containing oxygen versus iodide. This is a one-carbon alcohol. The red atom is oxygen. You can see that the red atom has a slightly smaller radius than carbon. Oxygen's just a little bit smaller than carbon. If we go back and take the same molecule and change the oxygen to iodine, iodine is now purple, and we put up a space-filling model, you can see how much bigger iodine is than oxygen. Atoms that are larger, and remember the trend down a column of the periodic table is size increases, right? Because you're filling a valence shell that's further away from the nucleus. Atoms that are larger necessarily spread out their negative charge through a larger area of space. And spreading out charge through space is always stabilizing. That size effect matters more than electronegativity. And that's general. The size effect matters more than electronegativity. This is my abbreviation for electronegativity. Matters more than the electronegativity difference when comparing different rows of the periodic table. Okay? So it doesn't matter that oxygen's more electronegative than iodide. What matters is that iodide is larger, and therefore its negative charge is more spread out. That means delocalized, and is therefore more stable, whereas the negative charge on the alkoxide is localized. Okay? So, size-based delocalization is often an important factor. Don't misapply that principle. We're talking about the size of the atom that bears the negative charge, not the size of the whole molecule. Okay, some people make that mistake, but make sure you're thinking about the size of the atom that bears the negative charge. Let me give you another example of a size of the atom that bears the negative charge comparison. Here is our friend, the alcohol. And here is a stinkier friend called the thiol. In chapter 3, next Wednesday, a week from now, we're going to talk about molecules that stink and molecules that smell like fruit and molecules that taste sweet or that taste tart or that taste like umami. For right now, thiols are sulfur-containing compounds that have an SH bond and they smell like rotten eggs. So kind of fun, skunk smell. Anyway, the pKa of an alcohol is 16. The pKa of a thiol, if you didn't know that, you would go to the pKa table, and right there in the middle is the thiol, and its pKa is 8. So we'll go down here. Which of these is more acidic? The thiol, right? Good. Draw the conjugate base. You got the alkoxide for the alcohol's conjugate base, and then this conjugate base happens to be called the thiolate. What's the difference between the alcohol and the thiolate? Sulfur is larger. Size is the thing that matters here. Sulfur is larger. Again, the negative charge is more spread out, more delocalized, and therefore the resulting conjugate base is more stable, which tells you that the corresponding acid must be more acidic. Okay? Go ahead.
So when we're calculating, I know that pKa's are calculated based on the data, but like the concept of why they're more acidic, is it basically actually based on their conjugate base then?
Yeah, so isn't that interesting? We're most of the time going to rationalize strength of acids. It's going to be easier for us to do that by thinking about the stability of the conjugate base. And the reason for that is, as organic chemists, we have a really good feel for what makes electrons more stable. Delocalization, being on an electronegative atom. So it's often easier for us to rationalize why an acid is acidic by thinking about its conjugate base. So when in doubt, draw the conjugate base. Okay, One more example of size, and this is maybe one that you've seen before. If you look at the halogen acids, HF, HCl, HBr, and HI, and you draw their conjugate bases, the molecule, the atoms that bear the negative charge once the proton is lost, you would see that the atomic radius of fluorine is much smaller, much smaller than the atomic radius of iodide. It's a huge difference. I just want to illustrate that in Spartan. There's the iodide. I'm just going to replace it with a fluorine, and you're going to see how small fluorine is relative to how big iodide was. So this makes a huge difference. The negative charge on fluorine is localized. The negative charge on iodide, why did I write iodide instead of larger? You guys just gonna sit there and watch me make a fool out of myself? Yeah, buddy, that's the idea. That's what we're paying for. The negative charge on I minus is more spread out, more delocalized. Why can't I spell delocalized? And therefore more stable. Correspondingly, HI is more acidic. The pKa of HI is minus 11. The pKa of HF is 4. So like, what's the number that comes after a trillion? Like, anyway, 1,000 trillion times more acidic HI is than HF. And HCl is more acidic than HF. HBr is more acidic than HCl. Interestingly, this size trend is exactly opposite of the electronegativity trend. F is most electronegative and I is least electronegative. So you can see that here electronegativity, when there's a big size difference, electronegativity isn't useful. Somebody asked during the first hour, okay, exactly what does the size difference need to be before I can ignore electronegativity differences? And I think they may have been hoping for sort of like a supply and demand curve where you have a function and you find the sweet spot. I don't know that there is such a thing. We're not going to do that. When comparing down rows, let's see, when comparing different rows of the periodic table, the size difference matters way more than electronegativity. When comparing across a row of the periodic table, size doesn't change very much, so electronegativity matters. Yes?
So when we're looking and comparing two different atoms, the more acidic one is going to be more stable. Is that correct?
When comparing two atoms, you said the more acidic one is the more stable. I think. Let me just put that into. I think that's an abbreviation of something, but there's a chance that if you memorize that, you're going to make a mistake. So, the strongest acid has the most stable conjugate base.
Okay.
And in this case, the strongest acid is strongest because its conjugate base is largest and spreads out the electron density best. Yes?
So the reason why delocalizing the electron makes it more stable is just because it lessens the negative charge in one spot, so it wants to get rid of it.
Right, so the question is, why does delocalization make electrons more stable? You can think of it probably decreasing electron repulsion if you spread it out over larger space. There's actually a beautiful but complicated quantum mechanical explanation for it. I will summarize. It involves the second derivative of the wave function, and what it means really is that electrons that are more spread out have lower kinetic energy. So you can accept that as fact. It's proven by the math, and we don't need to justify it. But yes, when electrons spread out, they have lower kinetic energy. Yeah.
Correct me if I'm wrong, though. In the past, I've been told that let's just take HOBr versus HOCl. HOCl is smaller, but it's more acidic than HOBr.
Yes. So this is actually a decent time to talk about that. That's kind of an esoteric example in the sense that we're not going to deal with molecules like this very much. But I think what you were saying is that you said HOCl is more acidic than HOBr. I want you to, I'm going to explain this in more detail later, but the short answer right now is it's not Cl or Br that holds the negative charge in the conjugate base. It's the oxygen. Yep. So that I've got an explanation for this, but this is a way not to, yeah, this is an example of how not to misapply the size issue. It's always the size of the atom that bears the negative charge in the conjugate base. Everything else's size is a secondary issue. And I will explain why this is more acidic than the other, but I'll do that in a minute. Yes?
Earlier you said that resonance also plays a role in
Yes.
delocalization. Which one is more?
So resonance versus size in delocalization. Generally, when we're using resonance as an explanation, the identity of the atom that bears the negative charge will actually be the same. Let me give you a couple examples of that. So here is our favorite alcohol, ethanol. It's just the easiest one for me to draw. Its pKa is 16. Now I'm going to draw a molecule called acetic acid. This is an example of a carboxylic acid. You will learn about that functional group on probably Friday and Monday. But acetic acid is a major component of vinegar. Vinegar is just water plus acetic acid. And by virtue of the fact that its name has acid in it, you assume that it's more acidic than the alcohol, and indeed it is, okay? By a factor of like 1 trillion, 10 to the 12. So let's look at their conjugate bases. The alkoxide has a localized negative charge. It's on oxygen. For acetic acid, the negative charge is also on the oxygen. We call this conjugate base of acetic acid acetate, or the acetate anion, because it's negatively charged. Notice that there's no difference in the size of the atom that bears the negative charge. It's oxygen in both cases. There's no difference in the electronegativity of the atom that bears the negative charge. It's oxygen in both cases. So what is the difference? Resonance, right? You would assume that the strongest acid has the more stable conjugate base. Now we simply need to explain why. And the answer is yes, resonance. Acetate follows a pattern of other molecules you've seen where you have a lone pair adjacent to a pi bond. And when that's true, you can delocalize the lone pair by moving it over to form a pi bond with the adjacent atom, and then breaking the other pi bond and moving it out onto the far atom to give you this resonance structure, where now it's the other oxygen that's negatively charged. These are the electrons that used to be on the negative charge on the oxygen. These are the ones that used to be in the pi bond. And what this tells you is, if we were to draw a hybrid structure, what you would see is that there was partial double bond character between each oxygen, and each oxygen evenly shared the negative charge. So this is called resonance delocalization. It allows the electrons to spread out through space, and spreading out is more stable. Okay, yes?
Couldn't you also look and see that the acetate is a bigger molecule, and so because of that?
Okay, so yeah, so the question is it also because acetate is larger?
Like, let's say there wasn't a resonance structure that was possible, but it was still a bigger molecule.
Right. If there was a resonance structure that wasn't a resonance structure that was possible, but it was still a bigger molecule, would the fact that the overall molecule was bigger matter? No. It's only the size of the atom that has the negative charge. Yep. Okay, so do you see the resonance stabilization of acetate? The fact that it's spread out in two places makes the conjugate base more stable, and that makes the corresponding acid more acidic. Okay. Yes?
What if resonance existed with an atom that was actually at a smaller atomic radius, but it existed, and then the other one, the negatively charged
Okay.
thing at it, that was just bigger in radius?
Yeah, so what if you have an interplay of multiple things? I can't think of a good example where resonance and size would interplay in the way that you're suggesting, but I can think of a case where resonance and electronegativity might both be factors. So let me set that up just a little bit. We kind of needed to talk about that anyway. So I told you above that, two things mattered for conjugate-based stability. Electron delocalization, we've talked about resonance, and we've talked about the size of the atom that bears the negative charge. And I've held off on this one, and I'm going to continue to do so for a moment. I want to talk now about how the electronegativity of the atom that bears the negative charge matters, when it matters. You've seen when it doesn't. When the size of the atom is changing dramatically, as it is as you go down a column of the periodic table, the size matters more than the electronegativity differences. But when you are within a single row of the periodic table, and you're comparing across that row, then electronegativity matters. And you can see this if we look at the acidity of various second row acids. So let's do this one. This is a sp3 hybridized carbon-hydrogen bond. I'm going to need more space. There we go. And its pKa, if you looked it up in the table, you would see that the pKa is 50. Its conjugate base has a negative charge on an sp3 hybridized carbon. If we move one space to the right on the periodic table, we now have this molecule. It's called ammonia, but it is an example of a molecule called an amine. Its pKa is 38, and its conjugate acid is this molecule, which is a negatively charged nitrogen that has 2 lone pairs on it. We'll call this an amide anion. We'll call the negatively charged carbon a carbanion. This molecule is called an alkane. I'm just writing these down so if I refer back to them, you'll know what I'm talking about. If we move one space to the right, you now have water, which has a pKa of 16. Its conjugate base is hydroxide with a negative charge on oxygen. And then if you move one space to the right, you now have HF, which I guess if I'm trying to be consistent with the way I've drawn things, which has a pKa of 4. Okay? Now, as you go across a row of the periodic table, size does decrease, but not by much in terms of percentage-wise, not by as much as going down a column. So across a row of the periodic table, size is not the major concern. In fact, across a row of the periodic table, the electronegativity is the major concern. So, and I need some more space, blah, 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 put that there. So notice that fluorine here is most electronegative, whereas carbon in this comparison is least electronegative. Notice that carbon, the carbanion, is the least stable conjugate base, and F minus here is the most stable conjugate base. Okay? So in a row, when size isn't changing a lot, then electronegativity of the atom that bears the negative charge is the best explanation. Electronegativity literally means the electrons on that atom are lower in energy than electrons on a less electronegative atom. At least within a row of the periodic table, that's what it means. Okay. So now, let's do an example where some of these things are offset. We're still coming back to this one. It'll be another few minutes. What if I'm going to draw this molecule, which is going to look like an alcohol. But it's different in the sense that the OH is adjacent to a pi bond. This molecule is called phenol, and its pKa is 10, and I'll draw its conjugate base. Now, is phenol more or less acidic than the starting alcohol? More. You can tell that because its pKa is lower. Okay? Let's see if we can think about why. What do you notice about the conjugate base of phenol, which we're going to call phenolate? What do you notice about that? You recognizing the chance for resonance structures because you've got an adjacent pi bond, right? So let's draw one of the resonance structures of phenol. I would move the electrons from the negatively charged oxygen to form a pi bond with the carbon of the ring, and then I would break this pi bond and move it out onto the adjacent carbon here. There are two other such resonance structures, and if you drew them, you would conclude that the negative charge can be in all of those places, delocalized. Okay? So the phenolate anion is resonance stabilized. The negative charge is delocalized. So that resonance delocalization explains why phenolate is more stable than this alkoxide, which explains why phenol is more acidic than ethanol. But what about the comparison with acetic acid? You might be tempted to say phenolate puts the negative charge in more places. That's better resonance stabilization than acetate, which only puts the negative charge in one other place. What's the difference between acetate and phenolate? What has acetate got that phenolate doesn't? Let's look at the atoms that share the negative charge in the resonance structures of acetate versus phenolate. What difference do you see? Both oxygens with acetate, both of them are oxygens with acetate, whereas in phenolate, 3 of the 4 places the charge can be are carbon. Why might it be better to have the charge on oxygen than on a carbon? Electronegativity. Okay, are you following that through? Isn't that nuanced, right? You're looking at resonance structures and then comparing where the negative charge is on the resonance structures. And that would lead you to conclude that phenolate is less stable than acetate because both are stabilizing by resonance, but at least acetate in so doing is putting the negative charge on oxygens, not carbons. Okay? Yes?
If phenolate was less stable than acetate, oh, sorry, I was looking at ethanol.
Yep, you got it. Okay, good.
That makes sense.
Yes?
Just a quick question. If you have negative charges, just say it's just hydrocarbons, and you have one that's connected to more carbons than the other, where would the negative go? On which carbon? When you have primary versus secondary and tertiary.
Well, I think you're asking the question, if you have a molecule like this and you want to draw its conjugate base, how do you know which proton gets removed? The short answer is there are differences in acidity. They don't matter that much because we will never really be trying to selectively remove one of these protons versus the others in a molecule that's just an alkane. Yep. All right. Oops, that's not what I wanted. We wanted to delete that. Okay. So lastly, there's, do you remember our list? We talked about electronegativity now, the atom that bears the negative charge. Now we're going to open the mystery box and return back to this issue of what other way of electron delocalization do we have? And this is illustrated with the example that somebody, that you brought up earlier, which was, and I don't have pKa numbers for this, so we're just, going off of, but I bet somebody could find them. We could ask Chad, I don't know. But HOCl is more acidic than HOBr, which is less acidic. So now let's look at their conjugate bases and try to figure out the more acidic one must have the most stable conjugate base. Let's figure out how the difference in the adjacent atom affects the stability of the conjugate base. Now notice the difference here is not in the atom that bears the negative charge. It's in an adjacent atom. Whenever I hear the word adjacent, I suddenly go back to Phineas and Ferb and the origin of the tri-state area, where somebody decided that the original bi-state area should be united with this other adjacent area over there. But anyway, that's adjacent, the adjacent atom. Here's where the argument comes from. Chlorine is more electronegative than bromine. And that will allow chlorine to pull electron density away from the nearby negatively charged oxygen through a bond dipole. And I think you represented this in 105, 106 with a symbol something like this, with an arrow pointing towards the atom that's electronegative and doing the pulling, and the plus end of the line sort of at the atom that's going to have electrons pulled away from it. Do you recognize that symbol? Have you seen that before? I can use that. You know what you're talking about? Okay. If chlorine is more electronegative, it is more able to allow the electrons in the oxygen-chlorine bond to lean away from the oxygen, and that should decrease electron repulsion with the negative charge on the oxygen, and that should also allow the negative charge on the oxygen to spread out. We call this sort of tug of war of electrons due to electronegativity the inductive effect. And it's not because of the difference in the electronegativity of the atom that is negatively charged, but it's a difference in the adjacent atoms and how they affect the electron density of the molecule. An example of that is acetate, acetic acid, which we've talked about. Its conjugate base acetate, and the pKa of acetic acid is 4. But if instead of hydrogens on the adjacent carbon you put fluorines, you make the molecule more acidic. You can put vinegar, acetic acid in water on your salad and it just tastes tart. You don't want to put trifluoroacetic acid on your salad because it's much more acidic. If it's concentrated, this will burn holes in your clothes. And in your legs? Lettuce, and in your lettuce. Okay, legs is certainly more grisly than lettuce, so we'll just go with lettuce. All right, why might this conjugate base be more stable? And the answer is fluorine is more electronegative than carbon. So fluorine causes the electrons in those carbon-fluorine bonds to lean towards fluorine. That makes this carbon a little bit more electron poor. In turn, that causes the electrons in this carbon-carbon bond to lean towards the carbon. The electrons in the molecule lean away from the place in the molecule that's negatively charged. That reduces electron repulsion, and it also allows the negative charge to spread out into more space than it otherwise would be able to do. So this inductive effect, which is due to the presence of adjacent electronegative atoms, is our other explanation. Electronegative atoms is our other explanation for acidity. Okay, so I want you to get familiar with this pKa table and using it to decide which acid is more acidic than another and which conjugate base is more stable. We're going to discuss next time how to use this information to predict what happens.